Hello everyone, I'm Hossein Mirzai and I'll be presenting our paper today. This project was conducted in and led by Professor Mackenzie W. Mathis lab. A Trojan attack makes a deep model look normal until a tiny trigger forces it to predict the attacker's chosen label. Think of it as a hidden shortcut embedded at training time that flips the output whenever the trigger is present. During training, a small fraction, let's say 5% of images are scanned with a trigger and falsely labeled as a target class. The model learns these hidden shortcuts, behaving normally on clean inputs, but at test time, any image containing the trigger is predicted into the target class. Trojans may enter through third-party model checkpoints. Since weights are hard to inspect, they pose a stealthy safety risk and security concern for real-world deployment of deep models. In response, several defenses have been proposed. Defense approaches seek to counter Trojan attacks by determining whether a model is Trojan, identifying the targeted class, and mitigating the Trojan if present. Because model weights are not interpretable, a common approach is to reverse engineer the triggers by optimizing in pixel space to reconstruct and estimate the triggers. Specifically, existing methods estimate triggers patterns by applying targeted PGD to images from a given source class. Without loss of generality, consider an image from class 0. The method targets each other class in turn, repeats this for all classes, and then compares properties of the resulting perturbations. For example, their norms are used to infer whether the model is Trojan. The intuition is that a Trojan model can be pushed to predict the target label with much smaller input modification compared to a clean model. Therefore, a smaller estimated trigger patterns indicate a higher likelihood of a Trojan. But in practice, these approaches have several limitations. High-dimensional pixel search often collapses to a generic adversarial noise, and adversarial trained or robustified models can inflate estimated triggers, causing false alarms and blurring the line between clean and Trojan models. Motivated by these limitations, we propose optimizing in the latent space of a pre-trained diffusion model rather than in pixel space. To begin, let me first review how guided diffusion model works. Guided diffusion models are widely used for multimodal generation, where a diffusion network synthesizes image condition on a pre-trained text model. Inspired by recent advances in this literature, we adopt guided diffusion for trigger estimation by replacing the text encoder guidance with the gradients from the model under test. Formally, we replace text-based conditioning in the reverse diffusion process with class likelihood guidance from the model under test. At each denoising step, we aim to increase the target class probability and decrease the source class probability. And finally, this is an overview of our pipeline where the diffusion model iteratively performs denoising condition on the classifier guidance. At each iteration, we also add uniform noise to reduce the likelihood of converging to generic trivial adversarial noise. After generation step, we use the estimated triggers for different defenses tasks, including scanning and mitigation of models. We compare this user scanning performance with several baselines. Tables A and B summarize results for scanning Trojan classifiers on backdoor bench and the TroJI datasets, highlighting the DISTIL's effectiveness on a scanning task. Prior trigger estimation methods are designed specifically for classifiers. We extend ours to object detectors by adding a guidance term during diffusion process. Particularly, we inject a gradient that increases the probability that each predicted bounding box center lands inside a randomly chosen corner regime. So the recovered trigger not only flips class predictions but also drags boxes toward corner. As a future research, we propose two directions. First, localizing trigger actions by combining inversion with saliency or feature attribution, which should increase the analyzed trust and enable targeted model scanning. Second, scaling DISTIL to other data domains like NLP and considering larger backbones such as foundation models. Thank you for reading our paper and watching this video.